NASA detected something impossible. A black hole 400 million light-years away is dragging spacetime itself into a spiral. Observations from multiple observatories captured a star's debris wobbling in perfect synchronization every 20 days as the fabric of reality twisted around it. And this confirms a prediction Einstein made over 100 years ago that scientists thought they'd never actually see. Right now, in a galaxy called LEDA 145386, a supermassive black hole with 5 million times the sun's mass is spinning so fast it's creating a whirlpool in spacetime, and we just watched it happen in real time. The accretion disk and jet system around this black hole are precessing, wobbling like a spinning top, with a period exactly synchronized to 2002 days across both X-ray and radio wavelengths. The jet is launching material outward at 99.7%, the speed of light, yet the entire structure is being dragged sideways by forces that shouldn't be visible at this scale. Radio observations from the Carl G. Jansky Very Large Array detected amplitude variations that repeated with less than 4% deviation over multiple cycles, precision that rules out random fluctuations. Dr. Cosimo Insera, astrophysicist at Cardiff University, stated in December 2024, "This is the most compelling evidence yet of lens-thirring precession. We're watching a black hole drag space-time along with it in much the same way that a spinning top might drag water around it in a whirlpool. Even more disturbing, this phenomenon only became visible because a star wandered too close and was violently ripped apart, creating the exact conditions needed to trace the invisible geometry of warped space-time. The tidal disruption event AT20T20 AFHD broke every observational pattern we'd seen in previous stellar destruction events. Here's what should concern you most. If space-time can be twisted this dramatically by spinning black holes, every assumption we make about gravity, orbital mechanics, and the stability of matter near these objects needs to be reconsidered. And there are billions of supermassive black holes doing this across the universe right now. Think about it. Before we dive deeper into this cosmic revelation, if you want to stay updated on what could be the most important confirmation of Einstein's general relativity in decades, don't forget to click the subscribe button and turn on notifications. Because what we're about to reveal will completely change how you understand the nature of spacetime itself. And leave a comment telling us, does this discovery make you question what else Einstein predicted that we haven't confirmed yet? Let's talk about what actually happened here, because understanding the sequence of events makes this discovery even more shocking. The story begins in 2020, when astronomers detected an unusual flash of light coming from a galaxy 400 million light-years away in the direction of the constellation Leo. To put that distance in perspective, the light we're seeing left that galaxy before the first dinosaurs appeared on Earth. The galaxy, catalogued as LEDA 145386, had been relatively quiet for years. Then suddenly, on March 14, 2020, multiple observatories detected a dramatic brightening. This wasn't a supernova. This wasn't a gamma-ray burst. The spectroscopic signature indicated something far more violent, a tidal disruption event. A tidal disruption event, abbreviated as TDE, occurs when a star makes the fatal mistake of wandering too close to a supermassive black hole. The star doesn't simply fall in. The gravitational gradient across the star becomes so extreme that the side facing the black hole experiences forces thousands of times stronger than the side facing away. This differential force literally pulls the star apart in a process astronomers call spaghettification. The star is stretched into a long strand of stellar material, like pulling taffy. The process is catastrophic and happens remarkably fast, typically within hours as the star crosses what's called the tidal radius. For the supermassive black hole at the center of LEDA 145386, with a mass approximately 5 million times that of our Sun, that tidal radius sits at roughly 100 million kilometers from the event horizon. That's about 2/3 the distance from the Sun to Earth. Any star crossing that invisible boundary is doomed. The star in this case was likely similar to our Sun, a main sequence star that had orbited peacefully in that galaxy for billions of years before its orbit decayed just enough to bring it into the black hole's kill zone. What happens next is where the physics gets fascinating. As the star shreds, its material doesn't fall directly into the black hole. Instead, it forms a rapidly rotating disk called an accretion disk. This disk can extend for millions of kilometers around the black hole, glowing intensely as friction and magnetic forces heat the material to millions of degrees. But here's where AT2020 AFHD became different from every other tidal disruption event we'd studied before. The accretion disk wasn't behaving normally. X-ray observations from NASA's Neil Gehrels Swift Observatory detected something unexpected. The X-ray brightness wasn't constant. It was oscillating, rising and falling in a repeating pattern. At first, astronomers thought this might be related to the chaotic process of material falling into the black hole, variations in the accretion rate, perhaps, or instabilities in the disk. That would be normal. But then radio observations from the Carl G. Jansky Very Large Array in New Mexico detected the same oscillation pattern. The radio emission was rising and falling in perfect synchronization with the X-rays. That's not normal. That's extraordinary. Radio emission from TDEs typically comes from the jets, narrow beams of plasma launched from the poles of the black hole at nearly the speed of light. X-rays come from the hot inner regions of the accretion disk. These are two completely different physical structures located in different regions around the black hole. For both to oscillate together in perfect synchronization means they must be physically connected in some way. They must be moving as a single rigid structure. Dr. Yanan Wang from the National Astronomical Observatories at the Chinese Academy of Sciences led the team that analyzed this data. Her team spent months examining the light curves, graphs showing how the brightness changed over time, looking for patterns. What they found was stunning. The oscillations repeated with a period of exactly 20.02 days. Not approximately 20 days, not around 20 days. Exactly 20.02 days, with a precision measured across multiple cycles that deviated by less than 4%. In astrophysics, when you see periodic behavior this precise, it's a signature of something fundamental. Orbital periods, rotation periods, precession periods. These are the rhythms of gravitational systems. The team ran computer simulations trying to explain what could cause both the disk and the jet to wobble together with this exact periodicity. Random variations in accretion rate? No. Those would create irregular fluctuations, not precise periodicity. Orbital motion of a binary companion star? No. The period is too short and there's no evidence of a second star. Precession of the entire disk jet system due to frame dragging? Yes, that fits perfectly. But here's where the story gets even more remarkable. Frame dragging, also called the lens-Thirring effect, is one of the strangest predictions to emerge from Einstein's general theory of relativity. Einstein first hinted at this phenomenon in 1913, though he didn't fully formalize it. In 1918, two Austrian physicists, Joseph Lense and Hans Thirring, worked out the mathematical framework. The concept is deceptively simple, but profoundly counterintuitive. When a massive object rotates, it doesn't just warp space-time around it. It drags space-time into rotation as well. Imagine a bowling ball sitting on a stretched rubber sheet. That's the basic idea of gravitational curvature. Now imagine spinning that bowling ball. The rubber sheet doesn't just curve. It starts to twist and spiral near the ball. This means that space-time itself, the four-dimensional fabric that combines space and time into a single continuum, can be set into rotational motion by a spinning mass. For objects like Earth, the effect is minuscule. Satellites in orbit around Earth experience frame dragging, but the effect is so tiny that it took decades of precise measurements to confirm. The effect causes satellite orbits to precess, to slowly change orientation, by only a few milliarc seconds per year. But for supermassive black holes, the effect becomes enormous. A black hole with 5 million solar masses, spinning at even moderate rotation rates, creates frame-dragging effects millions of times stronger than Earth. And if that black hole is spinning rapidly, which many supermassive black holes are, the effect becomes impossible to ignore. Here's what happens. Imagine the accretion disk around the black hole is tilted slightly relative to the black hole's equator. In normal Newtonian physics, that disk would just sit there, orbiting at whatever angle it started with. But in the curved, twisted space-time near a spinning black hole, something different happens. The disk begins to precess. Its orientation changes. It wobbles like a tilted spinning plate. And if a jet is being launched from the disk, which happens when magnetic fields threading through the disk channel material outward from the poles, that jet precesses with it. The entire system acts like a rigid gyroscope, wobbling around the black hole's spin axis. This is exactly what Dr. Wang's team observed in AT2020 AFHD. The 20-day period represents the time it takes for the disk jet system to complete one full wobble, one complete precession cycle. During that cycle, the disk's projected area as seen from Earth changes, modulating the X-ray emission. Simultaneously, the jet swings toward and away from us, changing its apparent brightness in radio wavelengths. The synchronization is the key. If these were independent processes, they wouldn't stay locked together. But because they're both responding to the same underlying cause, the twisted geometry of space-time itself, they move in perfect unison. Dr. Wang's team published their findings in the journal Science Advances in December 2024. The paper's title is deliberately technical: Detection of Disk Jet Coprecession in a Tidal Disruption Event. But the implications are anything but dry. This is the first time astronomers have directly observed frame dragging in action around a supermassive black hole. And it gets more fascinating. The team didn't just detect the precession, they used it to measure properties of the black hole itself. The precession rate depends on three things: the black hole's mass, its spin rate, and the geometry of the disk. By combining the observed 20-day period with models of accretion disk physics, they constrained the black hole's spin parameter. In general relativity, black hole spin is quantified by a dimensionless number between 0 and 1, where 0 means not spinning at all, and 1 means spinning at the maximum possible rate allowed by physics. The black hole in LEDA 1453886 has a spin parameter estimated between 0.6 and 0.9. That's a rapidly rotating black hole, spinning at 60% to 90% of the maximum possible rate. To put that in perspective, the event horizon of this black hole is probably completing one full rotation every few hours. That's a 5 million solar mass object spinning faster than Earth rotates. The energy contained in that rotation is staggering. Rotating black holes store enormous amounts of energy in the twisted space-time around them, energy that can theoretically be extracted through various astrophysical processes. But there's another problem that makes this discovery even more significant. Previous attempts to measure frame dragging around black holes had been frustrated by a fundamental challenge. You need a tracer. You need something orbiting the black hole that you can track over time to see the precession. For stellar mass black holes in X-ray binary systems, astronomers have detected hints of precession in the flickering of X-ray emission. But these systems are complex, and the signals are often ambiguous. For supermassive black holes, the challenge is even worse. Most of the time, there's nothing orbiting close enough and bright enough to serve as a clear tracer of the space-time geometry. Tidal disruption events solve that problem in the most violent way possible. When a star is shredded, it creates exactly the right conditions: a bright structured accretion disk and often a jet, both orbiting close to the black hole where frame dragging effects are strongest. AT 2020 AFHD gave astronomers a gift. For approximately 200 days, the aftermath of the stellar destruction provided a perfect laboratory for testing general relativity in the strong field regime. Dr. Burr Insera from Cardiff University, who co-authored the study, emphasized this point. This is a real gift for physicists. We're confirming predictions made more than a century ago, but we're also learning about the mechanics of the process itself. Here's where it gets really strange. The observations revealed something unexpected about how jets are launched. The fact that the jet precesses in lockstep with the disk suggests they're rigidly coupled. The jet isn't just randomly shooting out from the black hole's poles, it's anchored to the disk structure through magnetic fields. This supports models where powerful magnetic fields threading through the accretion disk get twisted and amplified, eventually channeling material outward in narrow beams. As the disk precesses, those magnetic field lines twist with it, causing the jet to swing around. The jet in AT 2020 AFHD was measured to be moving at approximately 99.7% the speed of light. That's 299 to 200 kilometers per second. At that velocity, relativistic effects become extreme. Time dilation, length contraction, and the beaming of radiation all come into play. When the jet swings toward Earth during its 20-day precession cycle, the radio emission appears brighter due to relativistic beaming, a phenomenon where radiation from near light speed sources appears amplified in the direction of motion. When the jet swings away, the emission dims. This creates the oscillation pattern observed by radio telescopes. The precision of the measurement is what's truly remarkable. Across multiple observing campaigns spanning months, the 20-day period remained constant to within measurement uncertainties. That's not something you'd expect from a chaotic system. It's the signature of an ordered, predictable geometric effect, the precession of a rigid structure in the curved space-time near a spinning black hole. But there's another aspect of this discovery that hasn't received enough attention. Frame dragging has implications beyond confirming Einstein's theory. It affects how matter behaves near black holes. It influences jet formation. It may even play a role in how supermassive black holes grow over cosmic time. If disk jet precession is common, if most tidal disruption events around rapidly spinning black holes show this effect, then our models of accretion, jet launching, and black hole feedback need to incorporate frame dragging as a fundamental component. Dr. Insera made an intriguing comparison. In the same way a charged object creates a magnetic field when it rotates, we're seeing how a massive spinning object, in this case a black hole, generates a gravitomagnetic field that influences the motion of stars and other cosmic objects nearby. Gravitomagnetism. That's the technical term for frame dragging when treated as an analogy to electromagnetism. Just as moving electric charges create magnetic fields, moving masses create gravitomagnetic fields. These fields are incredibly weak for everyday objects, but near black holes, they become the dominant effect shaping how matter moves. And here's the disturbing implication. If space-time can be twisted this dramatically, if the very fabric of reality can be set into rotation by spinning masses, what does that mean for our understanding of causality and the flow of time near black holes? In regions of extreme frame dragging close to the event horizon of a rapidly spinning black hole, space-time is twisted so severely that it becomes impossible to remain stationary relative to distant observers. You're forced to orbit in the same direction as the black hole's rotation, dragged along by space-time itself. This region is called the ergosphere. Inside the ergosphere, you cannot stop moving. Space-time is rotating beneath you faster than light can propagate outward, and you're carried along with it whether you like it or not. The implications for time and causality in these regions are profound and not fully understood. Time becomes tangled with space in ways that violate our intuitions. Now here's what makes AT 2020 AFHD especially significant. Most tidal disruption events show relatively steady emission over time. They brighten rapidly as the star is shredded, then fade gradually as the material is consumed. The light curves are smooth. AT 2020 AFHD was different. It showed short-term coherent variability, the 20-day wobble, superimposed on the overall brightening and fading pattern. When Dr. Wang's team first noticed this, they checked for instrumental artifacts. They verified the data reduction. They looked for contamination from other sources. The signal persisted. It was real. That short-term variability is the signature of frame dragging. It's the wobble of the disk and jet as they precess through the twisted spacetime. Dr. Wang stated in the Science Advances paper, such crossband, high-amplitude, quasi-periodic synchronous variability strongly indicates rigid coupling between the accretion disk and the jet, precessing like a gyroscope around the black hole's spin axis. The word rigid is important here. The disk and jet aren't wobbling independently. They're locked together, moving as a single system. This tells us something fundamental about the structure of these systems. The magnetic fields connecting the disk to the jet must be incredibly strong and well organized to maintain this rigid coupling as the entire structure precesses. Magnetic fields in accretion disks around black holes are known to be powerful, strong enough to launch jets at near light speed. But the degree of organization required to keep everything synchronized during precession is higher than many models predicted. And it gets worse. The energy requirements are staggering. To launch a jet at 99.7% light speed requires converting a significant fraction of the infalling mass energy into kinetic energy. That energy has to come from somewhere. One possibility, the rotational energy of the black hole itself. The Penrose process and its magnetohydrodynamic cousin, the Blandford-Znajek mechanism, are theoretical frameworks for extracting energy from spinning black holes via magnetic fields threading the ergosphere. If this is what's happening in AT 2020 AFHD, if the jet is being powered by extracting the black hole's rotational energy, then the frame dragging we're observing is directly tied to the energy source of the most powerful particle accelerators in the universe. Black hole jets have been detected shooting out for hundreds of thousands of light years, plowing through intergalactic space and affecting the evolution of entire galaxy clusters. The energy carried by these jets is almost incomprehensible, equivalent to the mass energy of millions of stars. And it may all be driven by space-time itself, twisted into rotation by spinning black holes. Here's where it gets really unsettling. There are billions of supermassive black holes in the observable universe. Most of them are probably spinning rapidly, either because they formed from the collapse of rotating gas clouds or because they've been spun up over time by accreting material with angular momentum. If frame dragging is a common and powerful effect around all of these black holes, then space-time across the universe is being twisted on enormous scales. Every quasar, every active galactic nucleus, every TDE, potentially all exhibiting this phenomenon, dragging space-time into spirals and whirlpools around them. We've only just learned how to detect it. We've only just confirmed it exists in one system, but it's probably happening everywhere. Dr. Huang Yang, associate professor at the University of Chinese Academy of Sciences and co-corresponding author of the study, stated, "This is the first time that disk-jet co-precession has been clearly observed in a black hole system, which is truly exciting. The word first is crucial. This is the beginning, not the end. Now that astronomers know what to look for, synchronized variability in X-rays and radio emission with precise periodicity, they can search for it in other TDEs, other active galactic nuclei, other black hole systems. The technique is powerful because it doesn't require ultra-high spatial resolution. You don't need to resolve the disk and jet visually. You just need to track their brightness over time and look for the telltale wobble. Now, let's put it all together. A star wandered too close to a supermassive black hole and was torn apart in a violent tidal disruption. The debris formed an accretion disk spinning at millions of kilometers per hour. A jet launched from the system at 99.7% the speed of light, and both structures began wobbling in perfect synchronization every 20.02 days as the fabric of spacetime itself twisted around the spinning black hole. The probability of detecting this effect without the precise timing provided by the TDE, without the star being destroyed at exactly the right time for us to observe it, is vanishingly small. We're not saying frame dragging is rare. It's probably ubiquitous around spinning black holes. But catching it in the act, with the right observations at the right time, with instruments sensitive enough to detect the subtle wobble, is extraordinarily fortunate. We've reached a point where even skeptical astrophysicists are acknowledging that general relativity continues to pass every test we throw at it, even in the most extreme environments in the universe. The European Space Agency and NASA have both allocated follow-up observation time to search for similar frame-dragging signatures in other TDEs. Over the next several years, we expect to find more examples of this phenomenon. And here's what this really means. Space-time is not a passive stage on which cosmic events play out. Space-time is an active participant. It can be bent, it can be twisted, it can be set into motion, and those motions affect everything happening within it. Every orbit, every trajectory. Every particle moving through regions of extreme curvature experiences the effects of this twisted geometry. Understanding frame dragging isn't just about confirming Einstein. It's about understanding how the universe actually works at its most fundamental level. So, what do we know for certain? First, astronomers have detected direct observational evidence of frame dragging, space-time being twisted by a spinning black hole, for the first time in a supermassive black hole system. Second, the effect manifests as a precise 20-day precession of both the accretion disk and jet, synchronized across X-ray and radio wavelengths. Third, this confirms predictions made by Einstein over 100 years ago and formalized by Lenz and Thirring in 1918. What don't we know? How common is disk-jet precession in other TDEs that we simply haven't observed closely enough? Can this technique be used to measure black hole spins across the universe? What are the implications for jet formation and black hole growth over cosmic timescales? And here's the urgency. AT 2020 AFHD has already faded significantly. Within the next year or two, the accretion disk will have largely dissipated and the jet will shut off. The window for detailed follow-up observations is closing, because if the next generation of time domain surveys like the Vera-C, Rubin Observatory's legacy survey of space and time detects hundreds or thousands of TDEs per year, and if even a fraction of them show this frame-dragging signature, we'll have a powerful new tool for mapping the population of spinning black holes across cosmic history. The truth is this: space-time can be twisted. Reality itself is flexible near massive spinning objects, and we've just learned how to watch it happen. And the only way to understand the full scope of this phenomenon is through continued observation of TDEs and other black hole systems before these cosmic laboratories fade from view. If this video left you questioning the nature of space-time itself, don't forget to click the like button and subscribe to this channel. We're tracking new tidal disruption events in real time as they're discovered, and you won't want to miss what happens when the Vera-C Rubin Observatory begins its systematic survey in 2025 and starts detecting these events by the hundreds. Leave a comment with your theory. If space-time can be twisted this dramatically, what other predictions of general relativity are we still missing? And share this video with anyone who thinks Einstein's theories are just abstract mathematics with no observable consequences. After watching this, they'll never think about black holes as simple gravitational wells again. They're engines that twist the very fabric of reality.